13th module of this lecture series. We will be looking into glass and timber, and today we shall mostly look into glass first as a material, then its mechanical properties. Most important for glass, use of glass in building is to is in the facade, in the windows as glazing, and therefore we look into solar gain factor and optical and thermal properties. Then we shall look into introduction of timber. So, we look into growth of tree and conversion. Right. So, let us see what is glass. As you all know, glass is a transparent or translucent non-crystalline substance made from silica, that is sand, soda, sodium carbonate and lime, calcium oxide or calcium carbonate. When heated, glass does not melt. It does not melt at a specific temperature. In fact, it softens, and if you remember your glass blowing laboratory exercises, you would know that once it is softened and becomes plastics, it can be molded by blowing, casting, rolling or extrusion. So, that is the specific property of glass, right. And when cooled, it again does not crystallize, it does not form, it is not a crystalline solid or solidify at a fixed temperature. All crystalline solids actually melts or solidifies at a fixed temperature, whereas glass does not solidify at a fixed temperature, and therefore, it can be thought of as a supercooled liquid with very high viscosity. It is a liquid with very high viscosity, so that it is not mobile, it is like solid. So, it can be thought of as a supercooled liquid with very high viscosity. Glass is amorphous, and we know that crystalline substances are opaque. If we look at the nature of the glass, glass is amorphous, and we know that crystalline substances are opaque, because the light gets reflected from the grain boundaries, right. They are very compact and compact structure, basically regular arrangement of atoms, and at the grain boundaries light will get reflected. Therefore, they are all opaque, right, whereas glass is not so, right. So, molten glass, if we cool it very rapidly, then this amorphous character is ensured. So, it is amorphous when we cool it very rapidly. If you cool slowly, then it will tend to become crystalline. We will have sufficient time to have regular arrangement of the atoms, and it would tend to be crystalline. But if you cool it very rapidly, then it remains as amorphous, and that is how it is actually transparent, because amorphous materials can allow light to pass through it. Now, if you cool it too rapidly, right, if you must cool it rapidly such that crystal formation is not there, but should not cool it too rapidly to induce what is called thermal stresses, to induce thermal stresses. Now, we know pure silica melts at 1700 degrees centigrade, and sodium carbonate and calcium carbonate, if we add them to the silica and then try to heat it up, then the melting point, of course, reduces down the melting temperature, and that is how glass formation takes place. But in any case, basically what contributes are the sodium carbonate and sodium oxide and calcium oxide, because we have seen in the glass formation we have finally will have only oxides, SiO2, sodium oxide, calcium oxide and other oxides. So, this carbon dioxide would actually evolve out at certain temperature, and since we have to break this carbon dioxide from both of these both of these compounds. So, you have to have lot of energy, and therefore, it is an energy intensive material. It is an energy intensive material. If you look at the main oxides in various glasses, there are other minor oxides, but we will only look into the main oxides. We will see in case of pure silica, of course, you have got 100% pure silica, you have got 100% pure silica, right, you have got 100% pure silica. But if you look at soda lime glass, silicate glass, then it will be about 69 to 74% silica, 12 to 16% of sodium oxide and 5 to 12% of calcium oxide. There are several other minor oxides present in this one, which I have just omitted for our purpose to understand that they are essentially oxides, and glasses are essentially oxides. Window glasses have typically about 72% of silica, 13% of sodium oxide and 10% of calcium oxide. Similarly, fluorescent tubes 71, 15, 4.6 and TV screens say 66, 8, and there are many other oxides, molybdenum, chromium oxides and so on, and borosilicate glass oven wares are 84. So, large amount of silica and other oxides. So, that is what the glass or typical oxide composition of glasses are. If you look at structure of glass, first thing, to add to color, we can add actually iron, manganese, copper, chromium, cobalt, nickel and similar other metal oxides are added to get color. So, color control can be, you can have different colors. For example, Fe can give you, Fe can, I mean by percentage control of Fe together with other elements, you can get green color or blue color and so on, I mean all of them together. So, oxides by metallic oxides contain the specific oxides, it can give you selenium oxides, etc., etc. In addition to this would give you specific color. So, color control can be done through this. Now, when you cool silica very slowly from its molten state, it crystallizes to gives you a crystal structure, let us say at a temperature Tm, which I call as melting temperature of the glass, melting temperature of the glass, like metal, like in case of metal, right. Okay. Then, but if you cool it rapidly, it will not be able to actually form this crystal structure. What is crystal structure? It is actually long range ordered molecular arrangement, long range ordered molecular arrangement actually. So, this long range order it may not be able to actually form if I am cooling it very rapidly, right. Long range order that may not be available if I am cooling it very rapidly. So, this change of structure in fact does not take place at the same temperature, rather takes place at certain lower temperature as we shall see, and that temperature we call as glass transition temperature. We shall see that it takes place at lower temperature and we call this as glass transition temperature. We call this as it takes place at lower temperature and we call this as glass transition temperature. So, at this point there is no latent heat evolution, and then you can say since it is much below the melting point, it is actually super cool. So, when you cool it slowly, cool it rapidly, if you cool it slowly you will get long range order and it will be crystalline, but if you cool it rapidly it will actually go below that temperature Tm and go to some other temperature which we call as glass transition temperature, where it will start hardening and there will be no latent heat evaporation. Since Tg is lower than Tm, it is as if it has got supercooled liquid below the solidification temperature. So, it is supercooled liquid below the solidification temperature, right. Right. So, continuing with that. So, if you look at the structure of the glass, it is like this. You see, this is the liquid from 1700 degrees centigrade as I said, and as the liquid I cool, this is the melting temperature. So, it should have, if I cool it slowly, at this point it would suddenly become solid, and therefore, the specific volume which is on this axis, specific volume, this will reduce. So, the sudden reduction in the specific volume, that is the change of state from or change of phase from liquid to the crystal structure, but when I cool it rapidly rather not slowly, cool it rapidly, actually it goes below this temperature, and this temperature is glass transition temperature, and the glass formation takes place from there. The structure would look like this. This is the crystalline structure of the long range order. Crystalline structure, you can see it is all orderly. The silicon and oxygen molecules, I mean oxygen atoms, they are arranged in regular order, it is all orderly. But if you see this, this is not as ordered as this one. So, short range order, and therefore, this is metastable, this is not stable. Crystalline structures are stable, that is what we have seen so far, and this is metastable, and this short range order, it is metastable, and it can change in the long range long term into crystalline structure, which we call as devitrification. So, this is what is the glassy structure, where the atoms are not arranged in regular order, as you can make it out from here. So, silicon and oxygen, they are not in same order, and this one is a regular order, which is crystalline structure. So, glass has the glassy structure, that is what it is, and that is how it behaves as supercooled liquid, because this temperature, below the melting temperature. So, you have cooled it below the melting temperature, and then it forms a high viscosity material or supercooled liquid, which it does not have mobility like liquid, and that is why you call it supercooled liquid. So, let us see some of the mechanical properties of glass. Stress strain behavior is important, after all. Even if I am using it in the windows, even if I am using it in the windows, then what will happen when I am using it in the even in the windows, let us say, then also if I am using in the windows, it has to withstand the transverse stresses, transverse load. Locally at least it should not fail. We do not expect glass to take care of the load of the structure, but it must sustain its own load, should be able to face the wind loading and so on, and therefore, stress strain behavior is important. Now, let us see what is the stress strain behavior of glass. This is the stress strain curve of glass. This is the stress strain curve of glass, and compare this with, let us say, alloy steel, which is something like this. Alloy steel is something like this. So, tensile strength, if you look at it, they have large ductility, that is what we have seen. In contrast, glass is elastic and low strain up to fracture, very low strain up to fracture. So, it is elastic up to fracture and low strain. Now, modulus of elasticity is much lower than that of those metals. Metals, this slope is, as you can see, modulus of elasticity, which is stress divided by the strain, is much larger in case of metal. It has got much lower values. Low fracture energy. So, area under this curve is also very small, because this strength is relatively small. The deformation is also small, but the modulus of elasticity is low. So, area under this curve is much small compared to something like this, which has got very large area. Low fracture energy, low elastic modulus, low strain fracture, and no plastic flow. There is nothing here. So, it is a brittle material. It is a brittle material, no plastic flow, and you can understand this from the fact that since in a crystalline structure you have grain boundaries where the dislocation stopped in case of metal. So, grain boundaries do not allow defect to perpetuate from one range, one place to the other. It kind of obstructs this perpetuation of defects, which are actually causing the deformation. Deformations are caused by movement of defects. Now, this would not be allowed by at the grain boundaries in case of crystalline material, but in case of glassy material, this is not the case, and therefore, quickly it fails at low strength, low strain, and therefore, this sort of property is there. So, it fails pretty early, right. More importantly, not only that it fails early, it has got low tensile strength, brittle, low less ductility, it is not ductile, and also low toughness, no energy, it can it has got low fracture energy. But another important issue is that the variability of results is very high in this case. Remember, we talked about the distribution of strength, relative frequency distribution of strength. So, here the same histogram, if you try to plot for glass, you can see the strength varies from 30 to 180 MPa, very large results, 30 to 180, it is a very large strength results, unlike metals, or even concrete does not show such wide variations. So, variations are very, very large. So, variability is also large, strength is also low. So, it is mechanical, it is not a very strong material. So, that purpose of course, we do not use, but you definitely use it for the purpose of other purposes like glazing material. That is where mostly in building it is used. If you look at its fatigue property is also something like this in order of megapascal. It does not have of course the fixed endurance limit as in case of metal, right, but 10 to the power 6 if you consider, this is how the fatigue behavior is, or SN curve is. SN curve looks like this, right. So, it has got a low fatigue strength also. So, from mechanical point of view, glass is not a very strong material, but it has got other important properties, and that is why you use it as a glazing material in case of building windows etc., because it has got certain specific good optical properties which you shall see, because we have said that it is a transparent material. Being amorphous, it is transparent or translucent material. So, it allows lights to come in, and let us look into some of these properties. First, let us look into thermal properties, because if it is put into the building facade, its thermal properties becomes important. Well, thermal properties are also important because it has to withstand the expansion contraction, thermal expansion contraction. So, let us see what about the thermal properties. It is a poor conductor, it is understood, because it is an amorphous material and would be a poor conductor, unlike crystalline metals which are a good conductor of both electricity and heat, and it is a poor conductor. So, its thermal conductivity is pretty low, but its thickness is usually low. So, thermal resistances are not very high, because you use very thin sections of glasses. So, effective thickness, since the low resistance of the glass or window glasses or glazing, that is not very high. Again, it allows a lot of heat to go in because thickness is also low, but its thermal conductivity is lower, right. Secondly, its coefficient of expansion is of this order, which is also low. Coefficient of expansion is lower compared to, let us say, steel, which is 11, and so it is somewhat lower thermal coefficient of thermal expansion. And since coefficient of thermal expansion is important from the point of view of its induced stresses under heating and cooling. So, under induced stresses under heating and cooling, right. So, this is what is about thermal expansion. Now, it is interestingly, you see, we talked about sometime when you are talking about walls, we said that surface finish we are talking about whitewash surfaces, and we said that whitewash surfaces has a very specific property, that actually it has got low absorption property to solar radiation, but it has got high long wave emissivity. Now, again let us recall this same thing. The sun's radiation contains large amount of short wave radiation, including visible radiation, which you can see, but terrestrial bodies which radiates at much lower temperature, something like 20-30 degrees centigrade, right, they actually radiate long wave radiations. Solar radiation has got a lot of short wave radiation. The radiation coming from, say, earth's surface, human body, or chair, table, furnitures, or similar other things, they are long wave radiation. So, long wave radiation, transmittance towards long wave radiation is also important, or it is of course in case of surface emissivity is important, but here how much of long wave radiation is transmitted through the material, that is important. Now, eventually glass has got an interesting property, it is opaque to long wave radiation while it is transparent to short wave radiation, and you would have heard of greenhouse effect. So, if you have a glass, it will actually can trap the solar radiation. So, heat can come inside the glass house, and it gets trapped, because once it is inside, this radiation hits up the material within that enclosure. If it is a glass enclosure is there, within that enclosure all the furnitures or whatever substances are there, they would be heated, and once they are heated, they absorb this solar radiation, they gets heated, and then they starts radiating the long wave radiation. Now, since glass is opaque to long wave radiation, this heat is in a way trapped. So, this can be well utilized in cold countries from to save energy for heating, right, or cold and sunny climate like Ladakh. You can use glass very effectively to see that sun's radiation is trapped, right. So, this is what we know as greenhouse effect. It is opaque to long wave radiation, while it is transparent to short wave radiation. So, this is an important property as far as glazing is concerned. Now, the property through which we actually define the two issues. One, it must bring in the light, because we said that building envelope acts as filter. It allows good thing to come in, but undesirable thing it just filters out. Now, from that point of view, the heat gain of the glasses are also important, because it is usually placed in the envelope of the building, and therefore, heat gain through the glass is also an important issue. And the property through which we measure this parameter or this factor, how much heat it will allow, the glass will allow to transmit, we call it solar gain factor. Solar gain factor is the ratio of heat admitted. Solar gain factor is the ratio of heat admitted to heat incident. Ratio of solar gain factor is ratio of heat admitted to heat incident upon the glass, right. All right. So, that is what we call as solar gain factor, right. Okay, if we see this solar gain factor, if you see this solar gain factor, you can see, say, let us say if 100% is incident, if 100% is incident here at this point, right, some of it will be reflected back and some of it will be transmitted, as some amount will be absorbed also. So, some amount will be absorbed also. For example, so in this case 100% is incident, 7% is reflected, some glass, and 80% is transmitted. What does it mean? 13% is absorbed here. Now, whatever is absorbed, this will be re-radiated in both this direction, inside and also outside, whatever is absorbed. So, absorbed ones, these are re-radiated. Now, how much is re-radiated? It will depend upon the type of glass, depending upon its molecular structure, etc., etc. 4% can be 4% can be irradiated inside, and 9% can be radiated in outside. So, in this case, how much is going in? Total is 80 plus 4, 84 is going in, admitted. So, I call 84% is admitted, and rejected is 9 plus 7, that is 16%. So, the solar gain factor in this particular case is 84%, 0.84. Solar gain factor will be 0.84 in this specific case. Similarly, for another glass, let us say 100% is incident, 6% is reflected out, because there is an interface. Reflection takes place from interfaces of two material having different refractive index, interfaces of material having different refractive index. So, here the interface of the glass and air, 6% will be reflected, 45% is actually transmitted directly. So, this is going in, but then 45 plus 6 makes it 50, 45 plus 6 makes it 51%. 49% therefore is absorbed, 49% is absorbed, and out of 49%, 34% is radiated outward, 15% is radiated inside. So, therefore, makes it 49, 34 plus 15, and therefore, total rejected is 34 plus 6 makes it 40%, and total admitted is 15 plus 45% is 16%. So, it is basically a heat absorbing glass. You can see this is a heat absorbing glass which actually absorbs about 49%, half of it nearly it absorbs, whereas this was not an absorbing glass, it was an ordinary glass. So, and heat absorbing glass, if its re-radiation is higher on the outer side. Now, in some cases re-radiation may be 50% inside and 50% outside. In such cases, absorbing glass are not really good. For example, if it would have absorbed 49%, nearly about 25% would have been admitted. So, 45 plus 25 would have made it 70% admittance, or solar gain factor being 70%. Anyway, so that is what is solar gain factor, and that is how actually glass admits energy. So, continuing with this thermal and optical property, we see that solar gain factor is one important issue which allows us direct transmission or heat to go in. So, we do not want, basically we do not want direct sunlight to go in. less energy should go in, its admittance or its solar gain factor should be low, so that heat does not go in. But the energy in the visible range, it must definitely it should allow to go, because light is wanted, natural light is wanted, that would make it energy efficient, would allow natural light to come in, but not direct sunlight, because which can cause what is known as glare, also it will bring in heat. So, direct sunlight or heat is not wanted. Direct sunlight can bring in both heat as well as it can result in glare, but diffused light or visible light as much as possible it should bring in. So, what you do, we can have some coating and treatment to ensure that solar gain factor of glass can be lower or modified to lower values, and then whole idea is that we allow as much as visible light possible while filtering the direct sunlight and heat. So, we do not want these two, because they are not useful for our purpose, but we do not definitely want visible light to come in. And as I told you, total heat admitted can be written like this: A into I into theta, where A is the area of the glass, A is the intensity of direct solar radiation, and theta is the solar gain factor. This can vary with angle of incidence as well. And how we calculate out the solar gain factor? It includes both the direct transmitted values plus also the re-radiated values, so both together. We shall see more of it in the next slide, Now, effect of this treatment, if we look at it, let us see, this is a 6 millimeter. Okay, first see what are the x axis. The x axis is wavelength, this is wavelength in the x axis. So, this is the total spectrum of the solar radiation actually, as you can see, and this is transmission coefficient, the direct transmission coefficient, direct transmission. It is not solar gain factor, we are looking at direct transmission. So, sun's rays you can see varies from 300 nanometer to about 2000, about 2200 or 2500 nanometer, 2200, actually it will be 2200 nanometer. So, sunlight varies from solar radiation is using this. Now, if you look at the transmission coefficient of sun's radiation, out of which actually this is visible range, visible range is 376 or something to about 780 or so is the visible range, visible range, the colors starting from violet to red. So, this is red, this side is a violet, red to violet. So, this is the visible range, right. So, this side is all our heat radiation, and this side is a long wave radiation. These are of course this is only the visible range. Now, if you see the transmittance in the visible range, the transmittance of this is infrared region as higher wavelengths, larger wavelengths, this is infrared, sorry, this is red and this is the violet infrared region, and if you go smaller wavelength, then the other waves will come in, electromagnetic waves, other electromagnetic spectrum will come in. So, we do not want this to come in actually. Now, if you see normal 6 millimeter absorbing glass, okay, just 6 millimeter glass, then this has got high transmittance here. So, it transmits most of the visible light, but it also transmits a lot of infrared heat radiations. So, these infrared radiations are nothing but heat radiations, So, it actually has got high transmittance value, something around 0.6, 0.65 etc. within this range also. Now, supposing I use 6 millimeter heat absorbing glass, it is a treatment basically, heat absorbing glass which can absorb a lot of heat. It has got high transmittance here, some reduction, but in this zone there is some amount of significant amount of reduction, right. So, transmittance actually is high here, absorbing glass are good, it does not absorb, it absorbs the heat, does not allow it to transmit, but whatever is absorbed, a part of it also would actually be re-radiated inside. So, admitted would be still high, but still this is a good solution, this is a better solution than having ordinary glass. If we see effect of coating, gold coated have got, you see again this is the visible range, this is where is the visible range, this is the infrared region, gold coated has got high absorptivity here, but very low absorptivity on the higher side. Nickel coated is something like this. Photochromatic glasses, which is sensitive to the light, it's actually the transmittance varies with the amount of light. So, it is actually photosensitive in a way, photochromatic glasses which will have bromide inside the glass itself, and this is its transmittivity is high at lower lower intensity of light, and it is low at high intensity of light. So, it tends to become opaque when light is it is very bright with a lot of sunshine, and when you have less sunshine, it's actually its transmittivity is high. So, this is photosensitive, sort of an intelligent glass, but either this coated or such photochromatic glasses are actually costly. They are not very cheap, but they can improve the properties significantly. Now, you can see the solar gain factor, it varies with the incidence angle. This zone is reflectance at, see this 0, this is your, that means it is normal. You have about reflectivity is about 0.6 or 0.7 in this particular case, this is ordinary flowed glass, and this transmitted amount is, this is absorbed, within this range is absorbed, within this range is absorbed, and this is transmitted. So, T is transmitted, T is transmitted, R is reflected. So, this height, this ordinate here, this is nothing but T represents this, T is this height, and R is this height, actually this height above this. So, in any case, in this case the R is this much. This amount is nothing but the absorbed amount, this amount is the absorbed amount, and part of it goes out, part of it comes out. So, this gives us the solar gain factor, this is actually theta, this is theta, solar gain factor line is here, solar gain factor line is here, right. So, this is solar gain factor, and as you can see, solar gain factor varies with the angle of incidence. This is for normal glass, ordinary flowed glass, this is for coated glass, the solar gain factor. So, solar gain factor varies with the angle, but treatment improves the solar gain factor for our usage purpose in the glazing. So, this is what was the optical properties of the glass, which are very important from energy efficient building design consideration, and also their solar gain factor or energy property related to thermal admittance of heat, that is what, or heat emission, that is what we have checked, right. Let us see how do it strengthen glass, because we have said that glass is, first of all, it has got low strength, it is brittle, it has got low fracture energy, and therefore, we would like to strengthen glass. So, we can strengthen the glass in some manners. One of the ways of doing it is through wired glass. In this case, wire is sandwiched between the molten glass at about 1050 degree centigrade. At about 1050 degree centigrade in the molten condition, actually this wires is sandwiched between the molten glass. So, that is why you strengthen, so that it cannot splinter out. So, if when there is a brittle failure takes place, the wire does not allow, it is a kind of reinforcement, one can think in terms of a kind of laminated reinforcement, and which will not allow it to actually splinter away. Toughened glass. Now, most of the since glass usually are in plate form, glass plate, and most of its defects comes from the fact that you create any kind of surface defect, there the stress increases very fast. You must be knowing that while cutting glass, one simply uses dents it with a diamond cutter. So, you make a line, that becomes a weak point, and there you can break it very easily. So, toughened glass, essentially what is done is air glass interface is placed in pre-compression, air and glass interface, because that is where all weaknesses starts. So, if you have interface that is in pre-compression, you toughen it, so that inherent flow, this should be FLAW, not inherent defect, basically inherent defect flow does not enhance the stress. So, any defect at the surface created, that should not enhance the stress. So, you pre-compress it, so that when some sort of tensile forces comes from outside, it would first will have to overcome this pre-compression, and then of course, it would be stressed. So, toughened glass are based on this principle, toughened glass are based on this principle. Now, this can be done by thermal treatment or by chemical process. thermal process precompression is done actually by heating it to 600 and 670 degree before it starts actually softening out and creating any stresses or cracks in the system. So, it is compressed, all defects are first removed and then compressed, and then chemical process by allowing larger molecules, for example, potassium instead of lithium in outer layer of the glass. So, by this kind of chemical or thermal treatment one can toughen this glass, right. One can use of course laminated glass, which we will look just in a moment's time. For example, this is what a toughened glass will look like. Now, this is the thickness of the glass, this is the thickness of the glass, this is the thickness of the glass, right. And if I look at the stresses, right, at this point this is compressive stress along this direction and tensile stresses. So, this is the thickness of the glass. Here it is all compression if it is thermally toughened. If it is thermally toughened, at the boundary it is pre-compressed to about, let us say, 75 MPa, because this is 100 MPa, 200 MPa. So, this is about 75 MPa both the surfaces. This is the surface of the glass, this is the surface of the glass, and you get actually pre-compression here, and its stress diagram is somewhat parabolic. Now, inside you have got, inside you can have tension. So, in case small tensions 50 MPa etc., and surface is actually pre-compressed, right. Chemically toughened glass will have pre-compression here over this length, and this is the small tension here. So, pre-compression here, and that can be very very large surface compression, but most of it is under very small tension. So, chemical, because here you have put molecules which are large, the atoms which are larger in size, and they change the structure and make it actually a kind of pre-compression. In case of laminated glass, we will discuss this of course about this lamination a little bit later on, transparent lamination. So, in case of laminated glass, same kind of toughening can be done by the thermal process, like this is about 3.5 MPa, and this is pre-compression, and this layer is also pre-compressed. So, strengthening of glass by thermally and chemically is possible. Now, this is the same thing, it can have different sort of pre-compression or surface pre-compression could be different. For example, in this one it is much higher compared to this. So, surface is compressed and inside is tension. So, it is compressed up to 80 MPa here, whereas inside it is 45, tension is this inside tension is 45 MPa, here it is 14 MPa is the compression, 7 MPa is the tension, and this is 2.3 millimeter low stress toughened glass and 2-3 millimeter high stress toughened glass. So, in case of laminated ones, you can have in fact different pre-compression or toughening, extent of toughening could be different. The inner one could be toughened more compared to the outer one, depending upon the situation. Now, this laminated glass to improve the toughness is something like this. This will have an inside core, and the leaves are the glass leaves. Even we have seen in the previous case also the similar ones. This is 2.3 millimeter, this is about 0.76 millimeter. Polyvinyl butyryl is the transparent material. So, this material 0.76 millimeter one can use in plastic, and this plastic is transparent, and therefore, it can be used to improve the toughness of the glass. So, what it will do actually, any failure of this one, it is toughened on both sides, plus any failure of this one, actually splintering will not be allowed. So, it is actually in a way reinforced and strengthened, right, to take further load. So, that is the idea about glasses. That is the idea about glasses, and we have understood that even if in buildings, of course, we do not use much of these toughened glasses, strengthened glasses, not much, but our main interest lies in glazing, window glazing, where the optical and the thermal properties are important, right, and you can have single glazing or double glazing, and double glazing with, in special cases, double glazing with vacuum inside, so that there is no heat transfer, it is completely insulated for window purposes, for in the case of used in the windows, right. Okay. So, basic thing is that glass should allow light to come in, but should not allow heat to actually penetrate. Alright. So, let us look into now timber, introduce timber to you, and which we will discuss their usage, some of the usage in details in the next lecture of this module. Now, timber comes from tree. Timber is basically process, it comes from tree. So, let us look at tree, the growth of the tree. Timber is the process, it is a material, comes from natural source, that is tree. Of course, the use of timber is getting restricted because from the environmental concern, because deforestation has resulted in several environmental problems. Therefore, use of timber are getting restricted, especially timber directly. However, processed timber still continues to be used to certain extent in construction and buildings, and therefore, for example, you must be aware of plywood being used as shuttering material in concrete construction, or their usage in doors and window frames. These are very common. So, therefore, we will discuss some of them right now. Timber is basically, the source of timber is basically the tree. So, let us see what the tree is, its growth. Crown, it has got three parts, as we shall see. Now, crown is the upper branches and leaves where chlorophyll acts as catalyst for photosynthesis and chemically binds carbon dioxide and water to form glucose. So, tree has got three parts, as we shall see in the next diagram. It has got three parts. One is the crown, next is the trunk, and the bottom is the roots. Timber comes from the tree. So, we are trying to look at the growth of the tree, how its structure is. Of course, one can go into details of the structures in molecular level and so on, which we will not be doing in this particular course, but we will try to see from the point of view of usage in construction. First, look into the tree, structure of the tree itself, and then some of the usage that would be there. So, it has got three parts, as we shall see in the next diagram. Crown is the top part, which actually has got upper branches and leaves, and the purpose of the leaves is it has got chlorophyll, which acts as catalyst, and you know that photosynthesis takes place, it can, in presence of sunlight, it acts as catalyst and chemically binds carbon dioxide and water to form glucose. Trunk is the next level, which supports the crown and conducts mineral absorbed by the root. The root absorbs mineral from the ground and transport it upward, the trunk transport it upward, and also stores and transport the glucose generated by the upper crown, generated in the crown by the leaves, transport and store it as required. Now, the point is, this part is also where you get seed. So, reproduction of the tree is possible from the crown part. This supports the crown and root supports the whole system. So, the diagrammatically it looks like this: the roots, the trunk and the crown, roots, the trunk and the crown. And let us look at the roots. Now, what does root do? Moisture or salt from the soil move upward, root subsystem, moisture and salts from the soil move upward. So, that is what root does. It gives you a firm foundation of the tree. It will not allow tree to actually fall down, supports it totally, and also collects minerals and salts, minerals and moisture from the ground, which it requires for its growth, and transports it upward. The crown, on the other hand, has got leaves, and what it does, in presence of sunlight during the daytime, it absorbs carbon dioxide from the atmosphere and then converts this carbon dioxide in presence of the moisture that has gone up. In presence of that, it converts into glucose, and that is the fundamental way how actually its energy is absorbed. In the solar energy is absorbed on the solar energy is actually absorbed first to the living being, right, and then of course the other animals or other living beings actually consumes this. So, this energy is then transmitted to the other living beings when one consumes this. right. So, this is what it is. So, from here this food movement, the glucose movement will take place downward, glucose movement takes place downward. In the night time, of course, the carbon dioxide is emitted out of this. Now, these junctions, from our structural point of view, junctions providing curl and burr. So, these are the junctions, right. These junctions, like this sort of curly grain structures, they come from here, curly grain structures come from these ones, right. Let us see the most important from structural point of view, which is the trunk. Now, the trunk subsystem looks like this. It has what is known as a center pith. This is called a pith. At the center you have a pith, center you have the pith. Then you have got this portion are known as sapwood. Sapwood is there in the periphery. Sapwood is there in the periphery. The inner, in the inner between the pith and the sapwood, you have heartwood. So, this is the heartwood. And what does sapwood do? Sapwood actually carry the minerals and moisture from the roots upward to the crown, and also transports the glucose downwards, right, and transmits it inside into the tree. So, purpose of the sapwood is to transport the food, right, to through the bust, and also inward as rays, right. So, if you look at the cross section, that is this portion of the trunk of the tree, this will give us idea. Trunk, even similar things are there in the branches also, because this is what is used mostly for making timber, right. Well, early wood structure will be like this, later wood structure will be like this. Now, tree grows radially outward from the center. As it grows radially outward from the center. So, growth rings takes place, growth rings takes place. So, this is one growth ring, the other growth rings, and so on. The outer periphery, outer bark, which is a protective layer. So, there is a protective layer, outer layer bark, and then there is a cambium between this inner bark or bust. So, this is a food conductive layer, inner bark or bust, BAST, which is a food conductive layer, and then you have cambium growth layer. This is actually the growth layer as the growth is taking place. So, food is moving inside and the growth would take place, and it will increase in its dimension. The dimension will increase. So, that is how it says its increase takes place ring wise increase takes place, right, radially outward. And therefore, from here, growth rings from here, the outer peripheral one is again the sapwood, as we have seen, through which essentially, so this is the sapwood is somewhere here, through which the food movements takes place, and the heartwood is already grown rings. Heartwood is already grown rings, and you can see, and pith is of course at the center, and you can of course see the structure. The initial wood structure would be, early wood would be something like this, and late, after sufficient growth, it will be something, growth structure will be something like this. So, that is what is the growth of the trees, that is what is the growth of the trees. Now, we have something called conversion, method by which actually trunk is sown is called conversion. You have the trunk and you got to cut it into pieces, cut it into pieces in order to make timber out of it, usually planks or battens. So, method by which trunk is sown is called conversion, right. There can be some sort of distortion caused by differences in shrinkage, because the moisture is an important criteria as far as timber is concerned, as we shall see, because its moisture content is very important, and as you dry off it can shrink. So, if there is differential shrinkages, grains not being, also grains are not parallel, they are not truly parallel to your cutting direction, therefore, some certain defects can come from conversion. So, let us see what we mean by conversion. Now, you can saw them like this, pieces like this, these are plain through and through sawing, this is called plain through and through sawing, and the properties that you get would depend upon how you have actually sown, depends upon conversion. Because as you can see, as we shall see further, that the material wise, it is actually cellulose fibers embedded in lignin. Timber would be cellulose fiber embedded in lignin. Now, the fibers actually extend along vertical direction. Therefore, the properties along the vertical direction and in the horizontal, because its growth was in the horizontal direction. So, the properties along this horizontal direction, radially outward direction, and properties along the vertical direction, they are unlikely to be same. So, therefore, timber is essentially anisotropic, it is not isotropic, you do not have same sort of properties in both the direction, it is anisotropic. Therefore, how you cut it is an important, its behavior or its properties that you get depends upon how you cut it. So, one way is to cut is cut through and through plane. The billet sawing would look something like this, you have cut, actually it is like this, and then pieces are brought in here, right, pieces are brought in from here, and once you have removed the bark, this this useful planks could be obtained in this manner. So, this is called conversion, right. Okay, this is called conversion, this is also part of actually conversion, this part of conversion, this part of conversion. So, commercial quarter sewing, this is called commercial quarter sewing. So, what you do, you leave this portion, central portion, cut pieces like this and cut pieces. So, there will be certain amount of and pieces like this. Then true radial sewing, so this is true quarter sewing, something like this is radial sewing, this is quarter sewing, this is normal quarter sewing, something of this sort of processes, and there will be certain amount of wastages depending upon the way actually you have done the way you have gone for the conversion, right, way one has gone for the conversion. Now, conversion can result in defect formation, because we said the grains are not always parallel to your direction of, they are not all parallel lines. Some places they will be parallel, there can be other kind of defects also present. So, what happens is you have this sort of from after conversion, you might find that because you have chosen the kind of conversion, you might find there is what is called wane or slope of the grain not being actually, it should have been something like this, rather the grains are something, it is not parallel, slope of the grain being different than the what there is a sloped grain. So, it should have been basically no slope vertically, and here also, and this is again not same, here you might find slightly higher, somewhere else you might find slightly different, and this defect can give you reduction in the strength or properties as desired. So, conversion is the process of sewing, and depending upon from the conversion process chosen, the properties differ, sometimes it can give rise to defects, right, and the planks are thus obtained from, planks or battens or whatever it is, they are obtained from this kind of conversion process, right. So, what we have looked into? We have looked into basically, as far as timber is concerned, we have essentially looked into the growth of tree today, and also we have looked into conversion. Now, from the growth of tree we have understood the trunk is the most useful portion from the point of view of timber, and we have also understood conversion, which is a method depends upon, it is a method of sewing actually, how you sew it and how you obtain the tree. Now, since it is a natural material, there will be several kind of defects present in it, and therefore, its properties many times may not be desirable. This is one issue. Second issue, in the process of just using it naturally as it is, there are a lot of wastages because of this conversion process, and we do not use every material together. However, processed wood, processed timber, if you process them in a right manner, use them in a judicious way in materials like plywoods, particle boards and so on, which we will discuss in the next class, they can be used more efficiently, and many of these defects which are present or they can be, you can take care of them in a more efficient way. One thing is to be understood, unlike most of the material that we have discussed so far, timber is anisotropic, its property along the direction of the grain and perpendicular to the grain direction, they differ, they are not same. Direction, their properties along the direction of the grain and perpendicular to the direction of the grain, they are not same. So, let us summarize today's discussion. We have actually discussed about glass and their properties, and we know that it is the most important glazing materials, and we have introduced timber. Next class we will look into little bit onto the material or molecular structure of the glass, of timber, and then followed by its uses in industrial timber products like particle boards, plywoods, etc., where we can use it structurally. I think with that we can conclude our discussion today. Thank you.